This is a... Okay. Sorry, having a audio problem here. Hopefully it won't go into a loop again. All right, so I am working having the Erica Synth educational series 5-step sequencer. And I've heard that there's a problem with the gate in where it requires a really high signal, more than 5 volts, which is what a lot of clock modules, that people use would put out. So I want to see if I can fix that before building this here. So I've got a little show and tell from what I learned today. Let's see. Okay, so here is part of the schematic for this this thing here, the sequencer. I originally thought that the way it was coming in, often with schematics that I've looked at, and I'm not an expert, there's a gate, the signal comes in, and then a transistor is used to act sort of as a comparator. So basically, if the voltage coming in crosses a certain threshold, then the transistor will act as a switch, and it will send voltage to whatever you want to receive the voltage. And so the way that works, the way I understand it, is you give it a reference voltage, and very often in the case of a microcontroller, which is those are the schematics that I was looking at, you'd feed it sort of a 2.5 volts. You'd feed it half of the voltage that you're giving to the microcontroller, since you have a linear voltage regulator, which is bringing the voltage down anyway. So then you just sort of split that in half, and that's your reference voltage, which is about 2.5 volts. And I think that's sort of a standard threshold to cross is like 1 or 2 volts for a clock. But so I thought, oh, easy, I'll just find that input and I'll just change the resistor value for the voltage divider, and then it will have a lower threshold. But that's not the case with this this particular module. Here's a close-up of that section. So here's the clock in. The way that it works here is the clock signal comes in, goes through a diode for voltage protection, I guess, here. This 100K resistor going to ground, that's a pull-down resistor, so that if no signal is coming in, the voltage won't float all over the place. It'll get pulled to ground. But because it's a 100K resistor, if any voltage coming in is coming in, then it will just it won't go to ground through that resistor. It'll go to the op amp to the right of it, because that's less resistance, because there's nothing there. That's how pull-down resistors work. So this op amp here, this is a TL074, which is your standard, most ubiquitous op amp these days, I believe. And the way this is pins 1, 2, and 3. So here's a schematic of the op amp. 1, 2, and 3 are the first of 4, because it's a quad op amp, first of 4 op amps. And so 1 is the output, 2 is the inverting input, and 3 is the non-inverting input. So the way that this is set up is like this. This is a traditional, classic unity gain, this is just the op amp in non-inverting configuration. So voltage coming into the positive input, which is the non-inverting input, it goes in the top there, and then it comes out, the output, and then you sort of do a feedback loop feeding it into the inverting input. And if there's no resistor there, sort of the way that we have it here, it looks like basically this is just creating a unity gain. So it's because there's no resistor, there's no change in voltage. This is just feeding in. It's I can't explain exactly how op amps work, but basically what's happening is it's coming into the non-inverting input. You feed the output into the inverting input, and it is basically a unity gain amp, meaning it spits out the same amount of voltage that comes in. So it's a buffer, basically. And the advantage of that is when you have a signal coming in, it's not going to cause extra current draw from whatever you're feeding into it. It'll just sort of balance it out. So anyway, then it goes into the clock input on the counter chip. This is a circuit of this is a I forget the number, but it's a counter chip. It's a CMOS IC integrated circuit that counts. And so every time it receives input on the clock, voltage going from low to high across the threshold, it advances the clock. So that's how the sequencer works. And there's a lot of detail on the Erica Synth's site about that, which is great. So, but what they don't talk about is what's going on here. So with this clock in, that's basically just going in there. So the voltage, this CMOS chip, this counter, this particular one will operate anywhere from 3 to 18 volts. So you can give it 3 to 18 volts. So in this schematic, it's just taking the 12 volts in from the Eurorack power, and it's just supplying that. So it's running at 12 volts. I looked at the data sheet, and I'm sure it's on there somewhere, but I couldn't find, where it said what the threshold is for the clock in. But if it's like other chips that I have experience with, it's usually about half of the voltage that you're running it at. So if it's 12 volts from the Eurorack, that means that 6 volts is the threshold. So that's why everyone needs a very high signal going in for their clock, because it's not your usual 1 or 2 or 3 or even 5 volts. It's over 6 volts that it needs in order to trigger the clock. And that's a lot. So people have, you have to use an offset or something like that to boost your clock signal, but that's, using up a module. And also all that an offset is an op amp, and you've got one built in here already in the path. So figured should be able to just boost the gain of that op amp, and that will help things out. So here is a schematic of what we want. So I was like, I said, what if you just have 2.5 volts coming in? This is the 1 volt, or the 1K, the pull down resistor. Wait, is it 1K? I think I messed this up in this. It's 100K. Anyway, it doesn't matter because it's just it's a pull down resistor. So the circuit should work the same way either way. So it's coming into the non-inverting input. So then if we add a 2 to 1, if this one is twice the voltage of this one up here is twice the voltage of this one going to ground, that's what we've got here. So it's RF and R2. Normally, if you want unity gain, I'm pretty sure that it's R2 has to be twice RF. I forget what the formula is. But anyway, if this one is twice as big as this one, then it will basically triple. You'll get 3 times gain. And so I mocked it up in Falstead here to see if that's true, and it seems like it's roughly right. So you have 2.5 volts in. If you put a 47K resistor there and a 24K resistor here, then coming out the other side is 7.5 volts just about. And at first I was just looking at smaller resistor numbers, resistor values, but then the current draw here was just wasting power. So here these are higher values, but they're still less than 100K. I asked some people who know more than I do, and they seem to say that was sort of the right value range there. So I'm going to go with that. My other things that I was looking at, my other concerns were, if you can see, looking at this schematic here, this is the part that we're dealing with, this op amp up at the top here. you can see going off to the top of the screen here, going into the switch, that is actually the internal clock. And so that's at the top here. This circuit here is another part of the quad op amp acting, it's generating a square wave, and you change your resistor value to increase the speed of the, or change the rate of the square wave. And so that's acting as the internal clock. And so that is coming down here. The internal clock is going, well, that's the gate out. Wait, that's not it. It's here. This is it. So that's the rate. That resistor there is the rate in this clock. It goes through this 1K resistor and down and into the switching jack here. So when nothing's plugged into it, when something's plugged into it, that's disconnected, so it doesn't matter. When something is plugged into it, or nothing is plugged into it, then this becomes the voltage source. That becomes the clock source going to here. So then the other thing I'm worried about is if this, I'm just going to assume that this is spitting out something like 12 volts because well, it might not be. I could figure it out, but it's going to be more than 6 volts anyway. We know that because it's working to advance the clock. So my concern was if will it damage this somehow to go through the op amp? It won't damage this. Nothing's coming back out that way. So the question is, would it cause any problems if it was going to boost hot signal even more? And I think the answer is no. I asked a couple people, and it seems like they agree that basically all that happens is if the maximum voltage coming out of this op amp will be the 12 volts. So even if you're sending 12, say it's 10 volts coming out of here, or even if it's 12 volts coming out of here, multiply that by 3, it's still going to clip. So it's basically that's like if you're cranking an amplifier and it maxes out, it's distorting it, it's clipping. But in the case of this clock, it doesn't matter. And so it'll just be no more than 12 going into the circuit down there. So that should be okay. And then beyond that, it doesn't matter because it's always going to be coming 12 volts coming out of there. I think this is right. So this is also an experiment because this might totally blow up. I don't know. But anyways, the way to add that, unfortunately, on this, well, let's see. Gonna look at let's get rid of this here. Click. Hope I'm explaining this clearly enough. As I said, I am not an electrical engineer. I just play one on EMS. So here is the op amp. You can see here it says TL074. So that's the op amp. Put it here, the little notch there indicates that, use a pen. The little notch here indicates that that's the top, which means that that's pin 1, pin 2, pin 3. Those are the pins we're dealing with. And you can see, if the light is right, that there is in fact a trace going between pins 1 and 2. There, that little bump is a connection. So we need to put a resistor between there. And then we also need to put a resistor going from 3, pin 3 there. Wait, where's the wrong one? Pin 3 there to ground. So look at the schematic again. Turn that window back on. Normally don't give presentations here. Okay, so yeah, coming out of 1, we need 1 between 1 and 2. We need to put that resistor. And then between 2 and ground, we need to put that resistor. So here's what I'm thinking. Also, if we look at that, we need to figure out the ground. The 1 and 2 is easy. We saw that trace. So now we need to figure out how to put, go between there and ground. So there is R14, this 100K resistor, the pull-down resistor. It's going to ground as well. So there's ground on that side of the resistor. So coming in here is one side of this resistor, and then on the other side is the other side of the resistor. I hope this won't mess anything up. But it shouldn't. I don't see why it would. So anyway, here's Here's 14. It's a vertical. That's not it. I can't do this upside down. Okay. That there is the resistor, R14. It's a standing resistor. It's going to be put in a vertical configuration. So that means the resistor is going to be standing up. But that doesn't really matter for what we're doing here. And then here is a little capacitor, or yeah, little like these capacitor deals here. So all that's going to have to get squished in. So first I thought, oh, I'd have to put this underneath the, where did that thing go? Lost it. Anyway, it needs to go underneath the pin socket thing. Where did it go? I lost the socket. Yeah, I'll find it. Anyway, so then I realized on the other side here, this is the other side. The pins will be sticking up. The pins from the socket will be sticking out there. And then between here and this side of the board, there's going to be a bunch of jacks and knobs and things like that, diodes. But there will be a space of 9 millimeters or so between this this board and the front panel. Here's the front panel, and then the front panel. This is the rate knob is here, and the switch is there. So we'll say the step count switch and the rate switch are there. You see. So that means where the op amp is and where the IC is, there's nothing. It's great. See, it's just blank panel there. So that means that there is space to add a couple little resistors, I think. So what I'm going to do is solder the socket there, then take my new resistors and attach them there. And I was considering using tiny little resistors, the surface mount ones, instead of these, because they would fit better. And then I thought, no, there's enough room, but now I'm reconsidering, because you can see that's a little big. Well, I'll figure that out. First I'll get the socket in place. So first what I'm going to do is I'm going to solder. No, first what I'm going to do is cut that trace, and I need to cut that trace as well, since we're routing a new one through. So for that, got an X-Acto knife. And then that's that for that. Oh, and then the other thing was that going from ground on one side of the resistor 14 here. So we're going to test this out. So focus, see what we're talking about. Okay, I've got my multimeter will make a beeping sound if there's a connection. So verifying that yes, between 1 and 2, pins 1 and 2, there is a connection. So once we cut that, we want there to be no beep. Now between this one, that's the output. No, this is pin. Sorry, this is pins 1 and 2. This is pin 3, which is going to the not ground side of resistor 14. Which is here, which is that, I'm guessing, and it is. Okay. So this other side is this is the other side of the resistor that's not there yet. So this then is going to ground. So when I put the resistor through the other leg of this, I'm not going to cut it at first, because that, between that leg there and this here is where we need to put the other resistor. This might be really tricky, but see what we can do. And hang on, I'm going to verify that in fact this goes to ground. That's ground. This is the power. Looks like the power socket. So any of these middle 6 pins should be ground. And yes, it's beeping. Great. Wait, did you see that? Yes, that was out of focus but in frame. All right. Now, cut the trace. Focus. All right. In fact, I'm going to zoom in. Can I do that? Oops. That was the wrong thing. There we go. Okay. 1 and 2. If this works, I'll be very happy. If it doesn't, I'll be pretty bummed. But good news is if this doesn't work, if I put it all together and nothing smokes, I didn't actually damage anything, then worst case scenario, I could just remove this resistor from the other side, both resistors, and just bridge these two pins, and all it should be as it was. And if things do smoke, then I will have to replace those things. But fortunately, there's nothing very expensive in this. Okay. Let's see if it worked. It did. Look. How about that? See? That pin, that pin. Nothing. Silence. Silence is the sound of success. Okay. Now turn on the soldering iron. What now? What next? The next step is to figure out what I did with those sockets. Arrgh, where did they go? I had them. Oh, they're right here. Huh. Standing by. Positioning. Okay, back this up since we don't have to see it quite so carefully anymore. Please excuse the reframing. Okay. Yes, the sockets were sitting right here, hiding right here in front of me. Okay. So I'm going to put both sockets in. Just actually, first I'm going to do the other components right around there. Normally you would put, let's see, let's take a look at the instructions. The instructions say, I usually start populating PCBs with lower horizontally placed components. In this case, these are the switching diodes, 10 ohm resistors, and the power protection diodes. Bend the resistor leads. That's how to solder. Okay, so these are all the same diodes. These are the classic, whatever they are, diodes. I'm only going to do the parts right around here. Get that done first, and then if that goes well, then the rest I'll just do it in order after that. Although not on this stream, it might be getting a bit long. That is a capacitor, not a diode. The only diodes to worry about are, turn this upside down, here. There and there. Okay. Power protection diodes to me. Place these first. I've decided I'm not going to do soldering streams in general, because usually when I do a soldering stream I get distracted and mess up even the simplest. Okay, so there, and the orientation is correct. You have to pay attention to the orientation. The little black line is a little line on the silk screen. Confirm that yes, in fact, it's the opposite direction for these two. So this goes here. I often place as many things as I can before soldering, just to save steps. There. Okay, so those two are in place. This is the fast forward a little bit if you're watching this on replay. Okay, so we've got those two, and then there aren't any other resistors right around that area, so I'll skip those for now. Okay, then the next thing is the dip socket and the ceramic capacitors. So, solder these first. Okay. Got a fan, fume extractor that I usually use, but it's kind of loud, so I won't right now. Instead, I will breathe in these lovely, lovely lead fumes. Okay. Since it's only a couple. Snip those off. Okay. Remove from the helping hands for the sockets. Okay, we've got two different size sockets. One with some and one with more. Okay, orientation. A little notch, making sure the little notch there is at the top to match the silk screen. It is. Do this one first. Just flip it upside down. One. Just hold it in place. Okay, I'm going to press on this while I reflow that corner. My phone is ringing. And then I'll do the rest. You know what? This might take a little while, so I'm going to stop streaming, answer the phone, and I'll be back.
Можливо, є якісь новинки, які